In this video, we will be discussing picturing data. Our learning objectives will be to draw and interpret bar graphs and pie charts. We will look at how to draw histograms and frequency polygons, and how to draw time series graphs. In the previous section, we talked about data and how to organize data, right? So now that we've gathered some data and we think that maybe some of it has an interesting story to tell, how can we most effectively present that data? In the previous section, we looked at how to display the data in table form using frequency distributions and stem and leaf plots. Those are very useful tools and perfectly valid, but they don't exactly pop, and they're using graphical tools to present your data can be a way of kind of taking things a step further and making it even easier to learn useful information from your data. To see this, let's take a look at a quick example. The data in the following table, supplied by the FBI, shows the number of hate crimes reported in the U.S. for the years 2005 to 2020. Okay. So here's a table of our data. Now, let's look at the same information presented in graphic form. So in my graph, I have the year along the horizontal axis, and then the number of hate crimes along the vertical axis. And you just plot your data, right? So it makes it very easy to see trends. The information is the same, but with the graph, just a quick glance is enough to see that hate crimes decreased significantly from 2008 to 2014, right? But then increased sharply starting in 2015, reaching a new high in 2020. Simply put, if you want your data to really catch someone's eye, you can't do much better than a nice graphical representation of the data. In this section, we'll study several methods for accomplishing this goal. We will begin by looking at bar graphs and pie charts. The first type of frequency distribution that we studied in section 11.1 was the categorical frequency distribution. When data are representative of certain categories rather than numerical, we often use bar graphs or circle graphs, which are also commonly known as pie charts, to illustrate the data. Let's take a look at these tools, and we'll start with a pie chart in our first example here, example 1. Okay. A pie chart is a circle that is divided into sections in proportion to the frequencies corresponding to the categories. The purpose of a pie chart is to show the relationship of the parts to the whole by visually comparing the size of the sections. So here's our example. The marketing firm Deloitte Retail conducted a survey of grocery shoppers. The frequency distribution below represents the responses to the survey question, how often do you bring your own bags when grocery shopping? So we want to take this frequency distribution and turn it into a pie chart. Draw a pie chart to represent the data. Before I do that, I want to add a little bit more information to my frequency distribution. Specifically, I am going to add another column, which I'm going to call percent. In this column, I want to express not just the frequency corresponding to each category, but the percent. Percent means out of 100, right? So it's a fraction out of a total of 100. This one's pretty easy to calculate the percents. I need to know the total number of people surveyed, which is not explicitly given in the problem description, but I have a frequency corresponding to each category, and if I add up those frequencies, they will add up to the total number of individuals surveyed. So 10 plus 39 is 49, plus 19 is 58, plus 32 is, they add up to exactly 100. Okay? Which makes it easy to calculate percents, because for each percent, what you're doing is you're taking the frequency from the category and you're dividing it by the total. And we want to, expressing that as a percent means multiplying it by 100%, right? So I'll just do the first one, and then I'll just write in the remaining ones because they're all pretty simple. But for the category always, you would take the 10, you would divide that by 100, and you would multiply that by 100%. These are easy because the denominator here is already 100, so this is going to work out to be just 10%. Okay. When the denominator is 100, it makes the calculation fairly simple, right? 10 out of 100, 10 over 100 is just 10%, right? So this one is 10%. The next one will be 39%, 19%, and 32%. Okay? And my percents need to add up to 100% as well. Okay? Now, we want to sketch the pie chart. Now, keep in mind that normally when things like pie charts and bar graphs are constructed, a software utility is used to do this, to make the graph clean and nice and constructed perfectly, right? So usually it won't be done by hand like what we're doing here. But it's worth kind of going over this as an exercise just to kind of see how this works, right? When you do the homework in ALEKS, I think there's only one problem where you're asked to make a pie chart, and basically what you'll be given a table where you have to fill in the percents, and then it has kind of a built-in graphing utility where it kind of creates the pie chart for you after you enter in the percents. Doing this completely by hand, though, you would need to use something that can measure angles, something like a protractor. Because remember that a circle, the total number of degrees around an entire circle is 360 degrees. Each of these categories is going to be represented as a slice, almost like a pie slice, right? That's why we call it a pie chart. And we need to figure out how big to make each slice. A protractor is something that can measure degrees. So we would need to figure out how many degrees correspond to each category, okay? We can do that. Down here, what we do is we basically calculate what percent of the total number of degrees. The entire circle is 360 degrees. So the category always would be 10% of 360 degrees. To calculate a percent of a total, we take the percent written as a decimal and multiply it by the total. 10% as in decimal form is 0.10. Okay. I multiply that by 360 degrees, and I get 36. Okay, that kind of superscript circled is the symbol we use to represent degrees. So the pie slice corresponding to the category always will have a size of 36 degrees. For never, it would be 0.39 times 360 degrees. And this works out to be about, I'm going to round these to the nearest whole number because that just makes it a little bit easier. That being said, there will be a little bit of error introduced because of rounding, but not very much. So this rounds to 140 degrees, which the slice corresponding to never. Okay. Frequently, this would be 0.19 times 360, and that works out to be what are we at? 68 degrees. Yeah. and then occasionally. Okay, this would be 0.32 times 360, and that works out to be 115 degrees. Okay. All right. So now that you have the number of degrees corresponding to each slice, then you can use a protractor, if you're sketching this by hand, to measure out the size of each slice. Your final result, though, is going to look like this picture right here. You measure those out, right? So the largest slice here is never, right, which has the number of degrees there is 140 degrees. Half would be 180 degrees, right? So 140 is a bit less than half, and 39% of the total. The second largest there is occasionally, which has 115 degrees, right? So never and occasionally are clearly the two largest. And then frequently and always are the two smallest categories here, right? So the important thing, though, is to make sure that your slices are sized properly, right? Because you want to get a clear idea of which categories have the highest frequencies, which ones have the lowest frequencies, and so on. And then it's helpful to also use coloring schemes to maybe make your different slices different colors as well. Okay, so that's one tool that we can use to graphically present data. The bar graph, or the pie chart, specifically works well for presenting data from a categorical frequency distribution. So while a pie chart is used to compare parts to a whole, a bar graph is used for comparing parts to other parts. Let's look at some different survey results that are better suited for a bar graph. So here's our next example. So let's revisit the marketing firm's survey of 100 grocery shoppers. Suppose the frequency distribution below represents the responses to the survey question, which grocery stores have you shopped at in the last month? So for this data, we want to draw a vertical bar graph for the results shown in the frequency distribution, and then kind of ask the question, would a pie chart make sense for these data? Why or why not? Okay. All right, so let's start by sketching the bar graph. So a bar graph, let's come down here. What we're going to do is a bar graph has a vertical axis and a horizontal axis. So let's start with something like this. Oops. Vertical, horizontal, and again, normally to make these really nice, we would use like a software tool, but sorry, let me make mine a little bit taller here. But we can do a rough idea, get kind of the sense of what these look like by sketching one by hand. So along one axis, you put the category names. And I'm going to choose to put the category names along the horizontal axis, although you could put them along the vertical axis. It's not really any rule saying that it has to be one way or the other. But putting them along the horizontal axis, I will have the category names, which are the grocery store names. So we would have Publix, Trader Joe's, Fairway, okay, Aldi, and other. And we'll just label this axis as grocery store, okay? Because this axis represents different grocery store types, different grocery stores. And then my other axis, this is the the vertical axis, this represents the frequency. Okay, and we'll just label this one, I'll just kind of write it sideways, visits by shoppers. Okay, so we clearly know what's being depicted here. What I need to do is I need to put like a numerical scale on here, and you need to kind of choose how to scale this. What I do know is that my scale has to go up to at least as high as the largest value in this frequency column, which is 65, right? So it has to go up to at least 65, and maybe a little bit higher might be good as well. Okay. So I think going in increments of 10 kind of makes sense, where 0 is at the very bottom, and then I go in increments of 10. Say 10, 20, 30, 40, 50, 60, 70. I'm going to stop at 70 since my highest frequency is 65. That seems reasonable to me. And then I put a bar or a column directly above each category name, and the height of that bar or column corresponds to the frequency for that category, right? So for Publix, the frequency is 50. So I'm going to put a bar that goes up to 50, like so. Okay. For Trader Joe's, the frequency is 40, right? So 40 is about here. Maybe you could sketch the top first and then just do the sides to make it a little easier. Fairway, we've got 28, which is just shy of 30. So I'm going to say that's probably right about here. Okay. Aldi, 33, so just a little bit above 30, a little higher than the Fairway one. Okay. Something like that. And then other is 65, right? So 65, we'll say that's right about here. Something like that. So my bar graph would look something like this. Okay. Okay, so how about the second question there? Would a pie chart make sense for these data? Why or why not? Okay. Okay, so there are kind of two good ways to decide that a pie chart would be a bad choice in this case. One is numerical. We were told that actually 100, I think it said 100, yeah, so 100 were surveyed, right? Remember in the bar graph example, I added up the numbers in the frequency column and they added up to exactly 100, and this represents the total number of individuals in the survey. If I come down here though, if I add up the numbers in the frequency column here, they add up to more than 100, right? So what that means is that we are not comparing distinct parts to a whole. The categories overlap, right? Some individuals shop at more than one type of grocery store. One person, maybe they shopped at Publix, Trader Joe's, and Aldi in the last month, right? So the same person would be represented in multiple categories. Okay. Yeah, and so the nature of the survey, which stores have you shopped at, pretty much guarantees that some people will choose more than one of the responses, right? Just the way the survey is structured tells us that the categories overlap. So yeah, that's really the reason, right? A pie chart only works for categories that don't overlap, right? Where individuals can fall into one category but not any others. Now, certainly I could have used a bar graph to represent the data in the previous example. You could have done that. That would have been fine. But what I can't do is take the data presented here and represent that as using a pie chart. Right, so data that works for a pie chart will also, you can also use a bar graph for that data, but not necessarily the other way around, right? So data that lends itself well to a bar graph may not work for a pie chart. And the main thing there is that individuals, for data that is used for a pie chart, you have to have a situation where individuals can only fit into one category and not multiple categories. Okay. Okay, let's see. Word of caution here in drawing a vertical bar graph. It's very important that the scale on the vertical axis begins at 0 and has consistent spacing. There is a section in your book, kind of a supplement on misuse of statistics. It's sometimes it's a common way to try to kind of doctor data or present it in a way that makes it look a little different from how it actually is. A improperly labeled axis can lead to a very deceptive graph. It can basically show data trends that look much more significant than they actually are. So that's just an important word of caution. Okay, moving on. In the study of statistics, it's definitely a good thing to be able to draw bar graphs. As a human being in the information age, it's a great thing to be able to read and interpret information from bar graphs. This doesn't sound particularly difficult when dealing with simple bar graphs, like the one we drew in example 2, but there are bar graphs that contain a lot more information and require some careful attention to interpret, like the one we are about to look at in example 3. So let's set this up. So this is reading a complicated bar graph. As vaccines for COVID-19 became available in late 2020, the Kaiser Family Foundation began a monthly survey of adults about their intentions in regard to the vaccine. The results are summarized in the bar graph, which is right here. Okay. Note that some percentages don't add to 100 due to undecided respondents. Okay, so 2 questions here. Describe trends among those who had already been vaccinated. And then B, which category was most stable from December to June? What can you conclude? Okay, so let's kind of take a look at this bar graph. So we have over here the months from December 2020 to June 2021. And we have a bar corresponding to each month. So these are our categories, essentially, right? These are our bars. Notice that when you put the categories along the vertical axis, the bars end up being horizontal instead of vertical. And then each bar is broken up into different categories, right? So, and those are represented by the different colors. So the light color here represents the individuals who have already gotten the vaccine. Red represents those who will get it as soon as possible. The yellow here is those who will wait and see. Kind of the turquoise will be those who will get it only if required. And then the purple here represents those who will definitely not get the vaccine, right? So you can see how these different opinions changed from December 2020 to June 2021. The first question, describe trends among those who had already been vaccinated, right? So that is the light color corresponding to each month. So the key at the bottom of the graph, okay, let's just kind of talk about this here, tells us that the people who had already been vaccinated is illustrated by the light. It's a very light green. Okay. No respondents had been vaccinated in December, right? December 2020, that was right when the vaccines were just starting to come out. The percentage progression by month was then 6%, 18%, 32%, 56%, 62%, 65%. This shows a clear upward trend in vaccinated respondents, with the most significant increase from March to April, where it jumped from 32% to 56%. Okay, so we'll just say a clear upward trend. Okay. Which category was most stable from December to June? What can you conclude? Well, if we look at this carefully, there were actually two categories that were quite stable. Those represented by the kind of the turquoise here and the purple. Right? Those correspond to people who would choose to be vaccinated only if required, and those who would definitely not get vaccinated. So it's reasonable to conclude that people opposed to vaccination had made up their minds early on and were unmoved as more information became available, right? That's a reasonable conclusion to draw based off of the observation that these categories remained quite stable. You do see some variation in these percents, right? 9%, 7%, 6%. Over here we vary between 15, 13, 14. That little bit of variation does not necessarily suggest changes in opinion, but it can more likely be attributed to just random sampling error. Because anytime you're dealing with a sample instead of an entire population, you'll see some variation that exists just due to the randomness of the fact that we're not using a complete entire population to represent our data set. Okay. So we might just say here that those opposed to vaccination remained unmoved as time went on. Okay, that's what we can most reasonably conclude from those categories. Okay, so we've already got the solution there. Let's move on and talk about histograms and frequency polygons. When data are organized into grouped frequency distributions, two types of graphs are commonly used to represent them: histograms and frequency polygons. A histogram is similar to a vertical bar graph in that the heights of the bars correspond to frequencies. The difference is that class limits are placed on the horizontal axis rather than categories. A consequence of this labeling is that there is no space between the bars, and that's because in a grouped frequency distribution, there is no spaces between the classes, the intervals. Okay? The procedure is illustrated in the next example here. So, in section 11.1, we analyzed and organized data representing the record high temperature in every state. It would therefore seem reasonable, if not expected, for us to illustrate that data graphically. Right, so that's just what we'll do. Okay. So let's do this. Let me just redraw the grouped frequency distribution. And this is exactly the one that we did in the example in the previous section, right? So if you need to review that section of the video, you can go back and do that. But we ended up with this. We had a column for class, and my classes were 100 to 104, 105 to 109, 110 to 114, 115 to 119, 120 to 124, 125 to 129, and 130 to 134. And then we had, I'm not going to put the tally column on. That's really only necessary for when you're first constructing it. But the most important pieces of information are just the class and the frequency. Okay, so the frequencies for the first class was 3, and then 8, and then 16, and then 13, and then 7, and 2, and 1. Okay. To turn this frequency distribution into a histogram, and I think I'll just try to put it right next to this so we can kind of see them side by side. What I would do is basically put my lower class limits along the horizontal axis, right? So I might say this is 100, 105, 110, 115, 120, 125, 130, and we'll go up here to 135 even, okay? My frequency would be along the vertical axis. So this represents temperature, remember that? Because these represent record high temperatures for each of the 50 states. And my frequency, I'm going to, again, so I have to do a numerical scale here, and we just want to choose kind of a reasonable scale to use, whether we're scaling by increments of 3 or 5 or 2, something like that. For this one, I need to just recognize that my largest frequency is 16, so my vertical scale here has to go up at least that high. And in that case, I would think that maybe going in increments of 2 might make sense. So like 2, 4, 6, 8, 10, 12, 14, 16, let's go up to 18, something like that, okay? And this represents number of states. I'll just say number of states. Right, so remember, 3 states had record high temperatures between 100 and 104, right? 8 states had record high temperatures between 105 and 109, and so on. So then, for each class, I'm going to have a rectangle or a bar, right? So it's basically a bar graph, but again, the bars don't have any gaps between them. So the first class has a frequency of 3. So I'm going to draw a bar that goes up to 3, that's halfway between 2 and 4, so right about there, okay? The next one has a frequency of 8, so it's going to be right directly next to the first rectangle. It's going to go up to a height of 8, like so, okay? The next one has a height of 16, so I'm going to go up to 16, something like that, okay? And then the next one has a height of 13. That looks like it's probably right about there, okay? The next one has a height of 7. That's right about there. And then 2, and then 1, right? This is not perfect. You want your sides to be pretty straight, and you want the width of the rectangles to be about this, to be the same as well. In my kind of quickly drawn hand sketch, there's a little bit of variation in those widths, but they should be all the same. Again, it's common practice to use like a software tool to help with this process as well. But this is the idea, right? So this is the histogram that corresponds to this frequency distribution right here. Okay, let's move on and talk about frequency polygons. A frequency polygon is similar to a histogram, but instead of bars, a series of line segments is drawn connecting the midpoints of the classes. The heights of those points match the heights of the bars in a histogram. In example 5, we'll draw a frequency polygon for the frequency distribution from example 4, so we can compare the two. So we want to draw a frequency polygon for the frequency distribution from example 4. So here is the distribution repeated again. I drew it out for you in the previous example, but here it is again. Okay. So To sketch a frequency polygon, one thing we need to do is we need to find the midpoints for each class. This is accomplished by adding the upper and lower limits and dividing by 2. Okay? So we have a total of 1, 2, 3, 4, 5, 6, 7 classes. That means we'll have 7 midpoints. Let's just make a list of them. We'll say midpoints. Ideally, I might put another column on my frequency distribution, but the way this is formatted makes that hard because they have the columns kind of broken up. So I'll just write it down here, okay? So for the first class, you would just take the lower and upper class limits, add them together, and divide by 2. Okay, so that would be 100 plus 104 divided by 2, which equals 102, okay? And we do that for all of them, right? So 105 plus 109 divided by 2 gives me 107, okay? If you did that same calculation for all of the classes, you'll end up with 112, 117, 122, 127, and 132. So there's my midpoints. So once I have the midpoints, then what I do is I come down here and I got, again, a horizontal and vertical axis. I'm going to label the axes the same, actually. I'm going to label this one temperature. And this one, number of states. And what I want to do along this axis is I want to plot the midpoints. So I'm going to say this is 102, 107, 112, 117, 122, 127, 132. And I'll scale the vertical axis the same as I did for the previous example. I'll start at 0 and go in increments of 2, 2, 4, 6, 8, 10, 12, 14, 16, 18, and so on. And then what I want to do is I want to, kind of like plotting ordered pairs, I want to plot a point corresponding to each frequency value and midpoint, right? So for the midpoint 102, that's the first class. It has a frequency of 3, right? So I put just a point right here. These points are basically corresponding to like the tops, the center tops of the rectangles in my histogram from the previous example. I think I should actually bring that down just a tad, so maybe right there. Okay, 107, my frequency there is 8, so I'll put that there. 112, that's the third class. It has a frequency of 16. Okay. 117, that has a frequency of 13. So right about here. 122, right, that is 1, 2, 3, 4, my fifth class. 1, 2, 3, 4, my fifth class here has a frequency of 7. Okay, so 7. Looks like about there. And then my sixth class here has a frequency of 2. And then lastly, a frequency of 1. Okay. I would extend my horizontal axis a bit more. I'm going to put 137 right here and 92 down here. Okay. Connect these with straight lines is what we do next. Okay, just straight lines. And then connect these down to actually touch the horizontal axis at those extended out points right there. Okay, so that's what my frequency polygon would look like. Okay. right there. Okay, so we've looked at pie charts, bar graphs, histograms, and frequency polygons. So generally, pie charts and bar graphs work for data that is categorical, and histograms and frequency polygons work for data that's more numerical, data that we can organize into these numerical classes like this. Okay. Let's look at another example here, identifying the value of frequency polygons. These two grouped frequency distributions that we're looking at down here, okay, come from data gathered in two calculus classes that I didn't teach, but somebody taught recently. Okay, one is for percentage on the final exam. The other is for overall percentage in the course. So it says to draw a frequency polygon for each distribution, put them on the same axes. What can you learn about final exam percentage versus overall percentage from the polygons? What would happen if you tried to draw a histogram for each on the same set of axes? Okay. All right. So for each, you have to find the midpoints. Now, of course, the nice thing is, let's just put a column over here, which we'll label midpoint. The midpoints are the same for both because the classes are the same, right? So for each, you're just adding up the lower plus the higher and dividing by 2. If I do that for all of those, I'm going to get 44.95. 54.95, okay, 64.95, 74.95, okay, 84.95, and 94.95. Okay. So what we would do is put my midpoints down here. Okay. So let's see. We've got 44.95, 54.95, 64.95, 74.95, 84.95, 94.95, and let's extend this up to 104.95 and down here to 34.95. Frequencies, let's see, the highest frequency on either column goes up to 20. So let's do increments of 2. This is 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, something like that. Okay. Let's start with this frequency distribution. The first one has a frequency of 3, so right there, and then 2, okay, and then 13, which is up about there, and then 14, which is just a tad higher, so right there, and then 14 again, which is right there. Let's see, did I miss one here? Oh, sorry, I'm off by a little. Hang on. Sorry, the first one actually needs to go over the 44.95, right? So height of 3, which is, yeah, right about there. 3 is between 2 and 4, so right there. Okay, then 2, and then 13, okay, and then 2 14s, and then a 12. Okay, so we connect these with straight lines. Straight line, straight, 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 straight. And then we connect down to the axis right there. Okay, something like that. Okay, the other one, the first one has a frequency of 0, actually. So that's going to be sitting like right on the axis. And then we have a frequency of 1, and then 7, which is there, and then it jumps all the way up to 20, and then 19, and then we have 11. Okay, so just below this one. So looks like we've got, okay, straight line there, straight line there, straight line there, and then we connect back to here and down to there. So there's my two frequency polygons on the same set of axes. There's a lot of observations you could make from the graph. The first thing that maybe jumps out is that there were a lot more students averaging in the 70s and 80s overall than on the final, right? And there were also more low scores on the final, which you can kind of see that from those trends as well, right? The number of students averaging in the 90s looks to be maybe about the same for both the final and overall. So those are just a few observations you can make, right? Are there other questions here? What would happen if you tried to draw a histogram for each on the same axes? If we try to draw two histograms on the same axes, we'd get basically a mess because the histograms have kind of filled in bars. Even if you use kind of different colors, in some places the bars would obscure each other, making it almost impossible to read, right? So that wouldn't really work. You'd have to do two completely separate histograms to make that work. Okay, so example 6 illustrates when frequency polygons are especially useful for making direct comparisons of two or more data sets. Okay, so I think lastly, we're going to talk a little bit about time series graphs. A time series graph can be drawn for data collected over a period of time. This type of graph is used primarily to show trends like prices rising or falling for the time period. The graph illustrating ID theft complaints at the beginning of this section is a good example. There are three types of trends. Secular trends are viewed over a long period of time, such as yearly. Cyclical trends show oscillating patterns. Seasonal trends show the values of a commodity for shorter periods of the year, such as fall, winter, spring, and summer. Example 7 shows how to draw a time series graph. Okay. So in example 7, politicians often talk about violent crime in the United States in apocalyptic terms, but what does the data say? The table shows the number of violent crimes committed per 100,000 citizens every 5 years from 1980 to 2020. Draw a time series graph for the data and use it to discuss trends in violent crime. Okay. So a time series graph, it's what you'll do is you'll just do, again, the two axes. In this case, we want to put the year along this axis. And this one will be violent crimes. Oops, so I can spell that correctly. And specifically, it is per 100,000 citizens. All right. So basically, we're putting the first row along the horizontal axis and the data from the second row along the vertical axis. Okay, so let's just put those years. We've got 1980, 1985, 1990, 1995, 2000, 2005, 2010, okay, 2015, 2020, okay. And over here we might go, I've got numbers that are kind of in the hundreds, so I might be inclined to scale these in increments of 100, but you still want to start at 0 here, so we go 100, 200. Let's figure out what my biggest number here is. It looks like the biggest number was 729, so that means I should probably go up to at least 800 here. Okay, so 300, 400, 500, 600, 700, 800. And really create this in pretty much the same way as the frequency polygon. Plot points and connect with straight lines, right? So 1980 corresponds to 596.6, just below 600. So I'm going to say right about there. 1985, 556.6, about halfway between 500 and 600, so about there. 1990, 729.6. Let's say that's about here, okay. 1995, 684.5, that's say about here. 2000, 506.5, just a little bit above 500, so about here. 2005, 469, a bit below 500. 2010, 404.5. Let's say that's about here. 2015, 372.6, about here. 2020, 398.5, so about here. And then connect those with straight lines. Which gives you a clear sense of the trends of the data, right? So what can we say? Well, from looking at the data, we can see that violent crime rose sharply between 1985 and 1990, hitting a peak in that year. Since then, it's been declining at a pretty steady rate. The two exceptions were a big decline from 1995 to 2000. Again, my graph is not perfect, but if it were perfect, you'd see this being a steeper line than this one. And then a slight increase from 2015 to 2020, right? But you see a fairly steady decline since 1990. Yeah, so that's basically a nice way to visualize the actual data to kind of back up what you might be hearing from somebody who's talking about this topic. Okay, so those are all the tools we wanted to cover for graphically representing data. So we'll wrap this video up. Thank you for watching.